Hey everyone, hi, this is Abhishek Mathur. I'm your physics faculty for JEE Mains. How are you doing everyone? I hope everything is going perfectly fine. I welcome all of you. I welcome all of you to this amazing session in which we are going to discuss the basics of nuclei. Welcome everyone. Welcome Rahul, Apoorv, Mayank. Welcome everyone. How are you all doing? Can you hear me everyone? Am I audible to all of you? Please reply in the chat box. I would like to hear it from you. Please do reply whether I am audible or not. You can also, rate the quality of broadcast from being worst for one and 10 for the best. Hey everyone, can you hear me? Am I audible everyone? Am I audible everyone? Rahul, Apoorv, Mayank. Hi. Welcome everyone. Welcome. So I hope you all can hear me. I'm audible to all of you, and let's proceed further. Let's proceed further. All right, mine. Thank you so much. Thank you so much for confirming whether I'm audible or not. All right, approve. Amazing. It's amazing to have all of you with us. All right, so Mayank, great. That's absolutely great, Mayank. So how's your studies going, everyone? How's your studies going? Do let me know. How's the preparation going for the exam, Ritesh? Amazing, amazing. So, how's the preparation going, everyone? You can rate it from 1 to 3. 1 if it's not going as per your satisfaction, and 2 if it's satisfactory, and 3 if it's going absolutely amazing. And I really hope that your preparation is going absolutely amazing and as per your plan. Hi, Ritesh. Hi. All right. All right. So this is a brief introduction about myself. Hi, this is Abhishek Mathur. I'm your physics faculty for JEE Mains here at Altedemy, and I'm a pass out from DTU. If you guys, all right, if you guys are engineering aspirants, you guys must have heard of DTU. It was formerly known as DC, Delhi College of Engineering. All right, so I completed my mechanical engineering from there, and afterwards I was associated with a very renowned institute for 4 years, and I have taught more than 2.5 thousand students over there successfully. And these are few hobbies of mine. When I was studying in college, I was really very passionate about vehicles and engines. All right, BV drawing and crafting. Welcome, BV drawing and crafting. Great. So this was a brief introduction about myself, and now let's talk about today's topic. Beta, today's topic is going to be nuclei. Nuclei is something which we guys have heard of and seen in our previous classes as well. When we were in ninth standard, we studied for the first time about Rutherford's model, and that is something which we will be discussing in today's closed course as well. We will be talking about atoms, and a brief introduction of atoms has already been uploaded. All right, so I hope you have seen this. So this is the topic of today's class. It is nuclei, beta. Tanmaya, Lenka. Tanmaya, welcome everyone. I welcome all of you, those who have joined in the class. Ruhan, by the way, is it for 10th class? No, beta, it is not for 10th class. It is not for 10th class, beta. This nuclear chapter is there in 12th standard. All right. So I welcome all of you. I welcome all of you. All right. So let's talk about the basic introduction about the nuclear chapter. See, what is nucleus? What is nucleus? We know that in an atom, there is this central part, and this central part is made up of protons, protons. It is made up of protons and neutrons, protons and neutrons. And protons are positively charged particles, protons are positively charged particle, and neutrons are neutral. They are neutral. They don't carry any charge. All right. So, when Rutherford conducted his experiment, he got to know that the center of the atom is very small in size, as most of the alpha particles passed straight through the gold foil. I hope you guys, Neeraj, welcome everyone. Neeraj, welcome. I hope all of you remember the Rutherford's gold foil experiment. Please reply in the chat box. Please reply in the chat box, beta. All right. So what Rutherford concluded was that most of the space, most of the space, most of the most of the space, most of the space in atom is empty, is empty, and its mass, nearly all of the mass is present inside the nucleus beta. This is our nucleus, this is our nucleus, and it contains nearly all of the mass, and it contains nearly all of the mass of the atom in itself. All right, and most of the atom is empty. This is something which we have learned from the Rutherford's model. All right, so in this chapter what we are going to study is, we are going to study the basic structure of the nucleus, the nuclear forces, and then we are going to discuss the mass defect, binding energy, and then binding energy per nucleon, and in the end we are going to discuss the very amazing and interesting topic, and that is going to be radioactivity. 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 Great. So this is going to be the last topic of today's lecture. So without further ado, let's start. So the first thing which we have to discuss, is the nuclear size. What is the size of the nucleus? The nucleus is really very small. The size of nucleus is very small, is very small, of order of order of order 10 raised to the power minus 15 meter. All right, the radius of the nucleus is given by this relation beta. It is given by this relation. And what is a here? What is a here beta? A is the mass number. A is what? A is mass number. Akash Sharma, no, this is not a one shot video. We will try to cover as much topic as we can in the first class, but if this topic does not get completed, we will make a second part. All right, Akash, I hope I have uh, answered your question. All right, so what is a beta? A is the mass number. What is mass number? Mass number is number of nucleons present in the nucleus. Number of nucleons means protons plus neutrons. Protons plus neutrons is equal to number of nucleons, and number of nucleons is mass number. All right, so the relation says that the radius of the nucleus is equal to r naught a raised to the power 1 by 3, where a is mass number and r naught is a constant beta, and the value of r naught is 1.2, and the value of the r naught is 1.2 into 10 raised to the power minus 15. See, this is a constant value. Irrespective of which nuclei you guys are talking about, this value is constant. This is a constant. This is a constant, and 10 raised to the power minus 15 is known as Fermi. Is known as Fermi. Just in case if you don't know this already. And then there is some data which I would like to share with you. See, we have a misconception that mass of proton and mass of neutron are equal. See, they are almost equal, and in most of the practical cases we are going to consider them as equal, but this is mass of electron, this is mass of proton 1.672622, whereas this is mass of neutron. So we can clearly say that mass of neutron is somewhat greater than mass of proton. This is something which we should know. Even though for all the practical cases we say that mass of neutron and mass of proton are equal, yes, they are approximately equal, but they are not actually equal. All right, and then this is atomic unit of mass. This is atomic unit of mass. When we talk about the mass of protons, electrons, and neutrons, we deal in U. What is U? U is unified unit, this unit U is used specifically when we deal with particles like electrons, protons and neutrons. All right, so its value in kg is this. See, you don't have to learn this. I'm just telling you that these values are not same. They are different from each other. Mass of proton is not equal to mass of electron. They are different. All right. And as you can see, this is the mass of electron. This is 10 raised to the power minus 27 kg. And for the case of electron, this is 10 raised to the power minus 31 kg. All right, great. Let's move ahead. Density of nucleus. See, density of nucleus is something which is really very interesting. Density of nucleus. See, we have an assumption here. We have an assumption here that the assumption is that we assume we assume we assume nucleus nucleus to be we assume nucleus to be a sphere. We assume nucleus to be a sphere. All right, and then we have to find density. What is density, beta? Density is mass by volume. Density is mass by volume. All right, so if we assume that mass of proton is approximately equal to mass of neutron, if we assume that mass of proton is equal to mass of neutron and let it be m, so mass of nucleus is going to be m. M is mass of one nucleon, and how many nucleons we are going to have? We are going to have a nucleons, because a is mass number. What is a? Mass number. It is not mass, it is mass number divided by volume. Volume is going to be 4 by 3 pi r cube. And from the previous slide, सर्वोत्तम बेटा, जो चीज समझ में नहीं आया ना, आप पूछ सकते हो हिंदी में मुझसे, ठीक है? मैं बता दूंगा हिंदी में, आई विल रिप्लाई। सर्वोत्तम, ठीक है बेटा? जो चीज़ जहां आपको समझ में नहीं है, आप मुझे पर्टिकुलरली बता देना, मैं उस चीज़ को हिंदी में समझा दूंगा, ठीक है? ऑलराइट, so from the previous slide we know that r is equal to r naught a raised to the power 1 by 3. So r cube is going to be r naught cube a. Put the value of r cube in the volume. This is going to be ma divided by 4 by 3. 3 is here, 4 is going to be here, pi. What is the value of r cube? It is going to be r naught cube into a. Alright, so beta a से a कट जाएगा, a will get cancelled from a. So one thing which we notice here is that what we notice here is that density is independent of a. Density is independent of a. What is a? A is mass number. इसका मतलब ये है कि अगर हम अलग अलग न्यूक्लियस की बात करें तो अलग अलग न्यूक्लियस का मास नंबर तो अलग अलग है, बट उनकी जो डेंसिटी है वो नियरली सेम है, वो कांस्टेंट है. It simply means that the density is independent of the mass number, and it doesn't matter what the mass number of the nucleus is, but the density is relatively constant. So density of the nucleus is constant, and it does not depend on the mass number. All right, great. So I hope you have understood this point, everyone. I hope you have understood this point of density of nucleus. So you don't have to learn the value. What is the value of density of nucleus? But there is one thing which you must know, and that is the density is independent. Density is independent of the mass number. All right. I hope that is something which is clear to you. If this is clear to you, should we move further? Sarvottam, do let me know if this is clear to you or not. Please reply in the chat box. Please reply in the chat box and let me know if this is clear to you or not. All right. So let's talk about nuclear force. Let's talk about nuclear force now. But a nuclear force is something which is absolutely amazing from my perspective. From my perspective, see, when you have learned about gravitational force, when you have learned about gravitational force, what do we say that? Gravitational force is responsible for the motion of the moon about the earth and the motion of earth about the sun. All right. So gravitational force is very important. Alright, and then in the first chapter of physics in your 12th standard, we studied about electrostatic force. Electrostatic force is a force which can be attractive or repulsive, and it acts between the bodies which have charges between them, which have it acts between two particles which carry some charge. Alright, so the force can be attractive in nature or it can be repulsive in nature depending on the nature of the charge which the two bodies carry. Alright, and when we discussed about electrostatic force, we must have discussed that how strong or how great this force is as compared to gravitational force. Gravitational force is a very weak force, but when we talk about electrostatic force is considered to be very strong compared to gravitational force. Alright, and now when we talk about alright, so before starting about nuclear force, let's also discuss one thing. I hope this is something which should have been in your mind yourself. See, we discussed that the size of nucleus is very small. It is of order 10 raised to the power minus 15 meter. This is the order of the size of nucleus. So can you imagine what is going to be the force between two protons? If I say that this is a proton and if I say that this is a proton, both these particles are protons, beta. They both are protons and the separation between them is very less. We know that the formula for electrostatic force is K q1 q2 by r square. If if r is very less, then then f is going to be then f is going to be large. Then f is going to be large, beta. Can you imagine? See, the value of r is really very small and we have to square it. So in denominator it is going to be 1 by 10 to the power minus 30. So can you imagine that how strong this force is going to be? It is going to be a very strong repulsive force between the protons. I hope you are able to understand my point, everyone. Please do reply in the chat box if you are able to hear me and if you are able to understand what I'm saying. Please reply in the chat box, beta. Please reply in the chat box. Sarvotam and others, Neeraj, Akash, Mayank, please, please participate in the class. Only then you are going to learn. Alright, so I hope you have understood my point that the separation between the protons is very less. So the electrostatic force of attraction should be very high. It means that these two protons should fly apart. It means that they should move apart, but it does not happen. We know that a nucleus is stable and all the protons, despite of the fact that they are being repelled by each other, they exist in that tiny nucleus without any problem. All right, great. Great, beta, great. So what makes this possible, beta? Nuclear force is something which makes this possible. Nuclear force is such an amazing force that not only it overcomes this force of repulsion between protons, it also acts between neutrons which do not have any charge particle. If you remember it correctly, the neutrons are neutral, they don't carry any charge. All right, so actually I'm just hearing, I can't understand much as I'm 10th standard. Okay, Ruhan, but still you must have learned about protons and electrons in your chemistry in 9th standard. So let's see how much you can understand. Try to understand as much as possible and do let me know just in case if you have any trouble. All right, Wuhan, is this clear? All right. So let's talk about nuclear force. Nuclear force. It is it is the strongest force. It is the strongest force in nature. See, out of all the forces which exist in the nature, this force is the strongest. This force is the strongest. All right. And the second point about this force is it is always attractive in nature. It is always attractive. It is always attractive in nature. It is always attractive in nature, and and it acts it acts between between all nucleons. All nucleons. It acts between all nucleons. It means that it does not depend on charge. I can write it in bracket: does not depend on charge. Does not depend does not depend on charge. It does not depend on charge, beta. All right. See, if I draw a nucleus here, and there are so many particles. There are so many particles. This is a proton. This is a proton. This is a proton. This is a proton. These are the protons. These are the protons, and and let's say that these are neutrons. Let's say these are neutrons. All right, these are neutrons. So nuclear force is attractive in nature, and it acts between proton proton, proton neutron, and neutron neutron. All right. Nuclear force is equal nuclear force is equal nuclear force is equal for nuclear force is equal for neutron neutron pair, proton proton pair, and neutron proton pair. But when we talk about net force, but when we talk about net force, we also have to consider the repulsive nature of the force between two protons. So when we talk about the net force, for for net force for net force, the force is the force is greatest between neutron neutron, and then neutron proton, and then least between proton proton. This is for net force, and this is for nuclear force. All right. In when we are talking about net force, we are also considering the electrostatic repulsion between positive and positive charge. Sarvottam, are you able to understand? Sarvottam, do let me know if you have any problem in English. I will repeat that particular part in Hindi. Okay, Sarvottam? Alright, great. And what are the other properties? What are the other properties? Other properties are that nuclear force, nuclear force, nuclear force is 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 short range force. It is short range force. It means that it acts in a very short range. See, the attractive nuclear force cannot act beyond the nucleus. All right. So it acts inside the region of nucleus only. It does not exist outside the nucleus. That's what this means. And the next point is going to be that it gets saturated. It gets saturated. It means that beta, that one nucleon is being attracted by its neighbor nucleons only. All right, it means that let me just talk about this particular nucleon. This particular nucleon is going to be attracted. This particular nucleon is going to be attracted by by these nucleons only which are surrounding it. All right. Nuclear force will not act between. Nuclear force will not act between. Let me just choose a color. Nuclear force will not act between these two. Alright, I hope you guys are understanding this. That the nuclear force gets saturated beta. That's why one particle is attracted by its neighbors only. Alright, great, great. So this is nuclear force, and these are some of the properties of nuclear force. Alright. So now comes a very interesting and amazing part, and that is mass defect beta. That is mass defect. What is mass defect? What is mass defect? What is mass defect? This is actually really very interesting. Uh, let's consider an example first. Let's consider an example. Let's consider an example first. Let's assume the case in which you have some vegetables inside a packet. You have some vegetables inside a packet, and then there is a case when you have vegetables. Great. Now consider this situation. This is really very interesting, everyone. You went to a shopkeeper, and when the shopkeeper weighed these vegetables, and they weighed the shopkeeper weighed these vegetables, and the reading came out to be 1 kg. And then the shopkeeper put all those vegetables inside a bag, and then again you weighed. Now when you are weighing these vegetables, you are getting that the weight, or rather mass I should call it, uh, mass is coming out to be beta, mass is coming out to be less than 1 kg. Isn't it amazing? Isn't it amazing beta? when the shopkeeper when the shopkeeper weighed these vegetables, the mass was 1 kg. But when you are weighing the same vegetables inside a poly bag, the result is coming out to be less than 1 gram. Is this clear to all of you, beta? Is this clear to all of you what I'm saying? Sarvottam, Ashish, Akash, Ruhan, are you able to understand this case beta I'm discussing? Please do reply so that I can understand whether you are able to get it or not. All right. So this is something which happens in case of mass defect. All right. See, in mass defects, when we have our nucleons, when we have our nucleons separated outside the nucleus, when these are nucleons when these nucleons are weighed outside the nucleus, their mass is something else. And when these same nucleons are inside the nucleus, and when these same nucleons are inside the nucleus, when they are inside the nucleus beta, when they are inside the nucleus, the result is coming out to be something else. This is our nucleus, this is nucleons. So it is seen that mass of nucleus is less than the combined mass of all the nucleons beta. All right. When we combine the mass of all the nucleons, when they are not inside the nucleus, their mass is greater than mass of nucleus. So basically situation is something like this. Individual nucleons carry more mass. Individual nucleons carry more mass compared to the mass of nucleus. So this is our mass defect. This is our mass defect. I hope you are able to understand my point, everyone. Please reply in the chat box. Please reply in the chat box if you are getting this or not. Rohan, Sarvottam, Ashish. All right, great. Now, see, this can be understood in two ways. When we have individual nucleons and we have to form a nucleus, all those nucleons will come together. All those nucleons will come together in a very tiny, very small space, that is nucleus. All right, so what happens is, when you will make those nucleons come close to each other, they will be proton and proton repulsion, but still you want them to be together, and this is something which they don't want. They are getting repelled from each other because proton and proton both are positively charged, but still you want to confine all those nucleons in a very small space. Now to do this you need energy. This is something which won't happen on its own, so you need some energy. All right, you need some energy. So the mass which has been decreased, when we see that the mass of the nucleons was greater than the mass of the nucleus, so where has the mass gone? Where is the mass which is lost? That mass is converted into energy. That mass is converted into energy. All right, or we can also say that if we have a nucleus and we want to break it into its constituent nucleons, when we have a nucleus and we want to break it into its constituent nucleons, we have to give some energy. All right, so I hope you have understood the mass defect. I hope you have understood the mass defect. What is mass defect, beta? What is mass defect? Mass defect simply means that mass of nucleons is greater than the mass of what? Mass of nucleus. All right. And what is binding energy? What is binding energy? See, this binding energy can be understood as energy that must be added to a nucleus to separate it into its constituent protons and neutrons. The total rest energy of the separated nucleons is greater than the rest energy of the nucleus. All right, this is something which we have already discussed. All right, if we have a nucleus and we want to break it into its nucleons, then we must supply some energy. We must supply some energy, and that energy is known as binding energy. All right, all right. The energy that must be added to separate the nucleons is called the binding energy. It is the magnitude of the energy by which the nucleons are bound together. All right. See, using Einstein's relation, delta E equals to mc square. I hope we all have heard about this. E equals to mc square is the equivalence between mass and energy, and it was given by Einstein himself. All right. So basically, what happens is we can find the binding energy. We can find the binding energy using this relation. Binding energy is going to be mass defect into c square. It is going to be mass defect into c square. Here delta m is what? Delta m is mass defect. Delta m is mass defect. All right, great. So let us understand the formula of mass defect in a different manner. As you can see that there is a formula written for binding energy. There is a formula written for binding energy, beta. The binding energy is simply found out using this relation. Now let's discuss it in a different manner. What is mass defect? Delta m. What is delta m? Delta m is mass of nucleons minus mass of nucleus. If we subtract the mass of nucleus from mass of nucleons, we get a mass defect. Alright, so what are mass of nucleons? If I say that, let us say that number of protons and number of neutrons are collectively A. So number of protons is going to be NP. Number of protons is going to be NP, and mass of proton is going to be MP, plus number of nucleons. Number of we can use a Z for this mass number. We can use Z for it, beta. Z MP, plus mass of nucleons. How many nucleons will be there? A minus Z. Mass of neutrons minus mass of nucleus, minus mass of nucleus. All right, great. Mass of nucleus. Now we can slightly manipulate this. We can slightly manipulate this and write the result in a similar fashion. All right. What we can do is we can simply add mass of Z electrons and subtract mass of Z electrons. Is this clear to all of you? This is something which we can do. We can add and subtract the same thing. It won't make a difference. Please reply in the chat box. It won't make a difference, beta. Now see, mass of protons, mass of neutrons, plus mass of electrons, it is going to be equal to the mass of the atom itself. It is going to be equal to mass of the atom itself. All right, mass of the atom itself. So this is going to be equal to this very same result which we have here. This is going to be equal to mass of Z protons plus mass of Z electrons is going to be equal to mass of one hydrogen atom into Z. All right, and this is mass of A minus Z neutrons, and mass of nucleus plus mass of electron is going to be equal to mass of that particular nucleus. So this is our delta M. This is our delta M, which is our mass defect. All right, this is a slight manipulation because we wanted to write it in the form of mass of hydrogen atom. This is mass of hydrogen atom, beta. This is mass of hydrogen atom, and this is mass of atom of element, the element which we were talking about. All right, so this is our mass defect, and now when we will multiply this mass defect by c square, we will get a binding energy. Great. See, there is one more thing which we must understand very clearly, that what is binding energy. Binding energy can be understood in two ways. First way is how much energy we need to give so that nucleons can combine and form a nucleus, and secondly, it can also be understood in a second way, that how much energy we must give to the nucleus so that the nucleus breaks into its constituent nucleons. All right, so binding energy, gives us an idea about the stability of the nucleus. The more binding energy we need to give, it means it's harder to break this nucleus. If a nucleus breaks with a very less binding energy, it means that it is unstable. It can be easily broken. It means it is not stable. So binding energy gives us an idea about the stability of the nucleus. All right. If the energy required is very high, if the energy required is very high, it means that the nucleus is stable and it will not break easily. But if the energy required is less, it means that it can be broken easily. All right. Let me write it here. Let me write it here that high value high value of binding energy means that nuclei nuclei is stable. Nuclei is stable. But later on, it was discovered that binding energy is not a very good criteria. What we must use is binding energy per nucleon. Alright. Binding energy is something which is defined for the whole nucleus. Right. We want something which is related to nucleons, and that is going to be binding energy per nucleon. Binding energy per nucleon beta. This is binding energy per nucleon is a better criteria. Binding energy, binding energy per nucleon is a better criteria for stability. If we want to judge the stability, then binding energy per nucleon is a better criteria. Now let's see a graph which depicts the binding energy per nucleon as the atomic number increases. On the x-axis we have our atomic number. This is atomic number and this is binding energy per nucleon. Binding energy per nucleon. All right, let's discuss this graph. See, the first element is hydrogen. The first element is hydrogen. No, this is not. This is an isotope of hydrogen. See, this graph shows the variation of binding energy per nucleon. What we must know from this graph is that iron Fe has the highest value of binding energy per nucleon. Binding energy per nucleon. All right, wait. So let's talk about nuclear stability and radioactivity. What is nuclear stability and what is radioactivity, beta? See, even though the number of elements which exist are less, but the number of nuclides. What are nuclides? Let's discuss this. Nuclides means nucleus. It means nucleus. It means beta nucleus. There are about 2500 nucleuses which exist in our universe, and only about 300 of them are stable. All right, so in fact the number of elements are very less, but the number of nucleus which exist are very high, and only a small proportion of them are stable. All right, so what happens is the nuclei which are unstable, what they do is over the period of time, either they will combine. When they will combine, it means that they are fusing together. It means that nuclei are fusing together, beta, and that reaction is known as nuclear fusion. And if the nuclear size is very large and the nucleus wants to break. See, from the previous graph, if you will see that if I take an element somewhere here, its binding energy per nucleon is less than to an element which is here. So what will happen, this particular nucleus will try to break itself. this particular nucleus will try to break itself, so that binding energy per nucleon per nucleon can increase. Right, it wants that the binding energy per nucleon should increase. Basically, an element is an nucleus, a nucleus is stable if its binding energy per nucleon is high, and to do that it will break its size, it will break itself, so that binding energy per nucleus can increase. All right, so this process in which a nucleus breaks itself, in which a nucleus breaks itself or fuses together, is known as radioactivity. It is known as radioactivity when nuclides combine or break, emitting particles, and electromagnetic radiation is also formed. You guys might already know that sun is the case in which nuclear fusion is happening, and we are getting electromagnetic radiation from sun, and ultimately sun is the only source of energy which we guys have. All right, great. So here's another graph. Here's another graph which is known as Sagre's chart. Which is known as Sagre's chart. What we have done is we have plotted number of neutrons and number of protons here. This is number of protons, number of protons, and this is number of neutrons, number of neutrons. So in ninth standard, when you might have learned the elements from atomic number 1 to 20, you might notice that in that case the number of neutrons and number of protons are nearly equal. The number of neutrons and number of protons are nearly equal. For small value of a small value of a number of neutron and proton are equal nearly. Either they are equal or there is a difference of 1 or 2. But as the atomic number increases, as the value of a increases, you will notice that as a increases, you will notice that n increases more. N will increase more. See this dotted line represents n equals to z. But you will see that actually the nucleus which exists in nature, see, it is bending something like this. So number of neutrons are increasing, and this is something which should happen. Why? Because if number of neutrons and number of protons are increasing an in the same manner, then the repulsion between proton is going to be very prominent. It will increase. All right, to reduce the repulsion between proton and proton, number of neutrons increase faster, so that it can occupy the space between the protons. All right, great. Great. Now let's discuss briefly about radioactivity. What is radioactivity? Radioactivity is the case in which a radioactive nuclei will decay itself. All right, a radioactive nuclei will decay. Even you might get surprised, but a body also consists of a few radioactive nuclei of carbon 14 and potassium 40. These are radioactive, and they are present throughout a body. So when we talk about radioactive materials now, see, what we are talking about those radioactive materials which are generally used for bombs, right? But it is not something which is not happening in our surrounding. Right, please make a note of it, that radioactive elements are harmful when they are used in a certain way, and if we go to a place where they are present in abundance, all right, so we should avoid that place, all right. But in nature, in our surrounding also, in fact our body also have radioactive materials, radioactive nucleus, all right. In fact, I don't know if you know this or not, but lead is also, radioactive, radioactive, and it is used in batteries. It is used in batteries. It is used in batteries of a car and the inverter batteries which we guys have at our home. All right. So, uh, let's keep our lecture for here only. We will discuss the remaining part of the radioactivity. We have hardly started radioactivity, and then we will have to solve a lot of questions of radioactivity. We will do that in tomorrow's lecture. And so let's hope, I really hope that all of you will be present in tomorrow's lecture as well, and we can solve all the questions. And just in case if you have not joined our Telegram channel yet, I would like to request all of you to please scan these barcodes. The first barcode is for our Telegram channel. Please join our Telegram channel and stay connected with us so that you can get all the important links for the webinars like this, and you can always join those free webinars without missing them. All right. And the second barcode is for the Telegram chat. Once you will scan this particular barcode, you will be able to join the group of Altedemy JEE chat box, where we can have conversations regarding your doubts and all your queries can be resolved. All right. All right. So, and please, it's my humble request, if you have not already subscribed to our YouTube channel, please subscribe to our YouTube channel so that you can get all the lectures on time and you don't miss on anything. Please subscribe to our YouTube channel. It also motivates us, and when you will motivate us, we can do much better, for you guys only. All right. We will be providing a lot of quality content for free so that you guys can reap the benefits of it. And then let me give you a brief idea about the course which we guys offer. You will be getting nearly 150 plus lectures which we have recorded for you guys. And then our educational platform is so convenient. You guys will be getting an introduction video of the topic which will be discussed in the class. All right. The introduction video will be uploaded before the class itself, so you can get an idea of what we are going to discuss in the class, and you can get an idea of all the topics which will be discussed in the class. All right. And this syllabus is prepared by JEE experts, those who are associated with the industry for a really long time. And we have a flipped classroom method, which basically means introduction video will be given beforehand. Introduction video will be given beforehand. All right. And then there will be doubt solving sessions where we guys can solve the doubts in the class itself. Someone told me that we don't study about additive elements because they are making. No, actually that's not the case, beta. That's not the case. All right. So how our classes work, let me give you a brief idea. You guys will be getting all the theory which will be prepared by the experts, and you guys will be getting it beforehand. All these study materials will consist of quality questions specially prepared, consisting of all the kind of varieties which are asked in the exam. And we guys also provide free webinars like this which you have just attended, and you guys will be amazing questions for homework so that you can check your progress. You can check your progress, and then your homework will be checked then and there, and you will get to know how many questions which you have attempted are correct or incorrect. All right. All right. So we have three kinds of program beta. The first one is light, and the second one is smart, and the third one is proficient. When we talk about the light program, you guys will get interactive live classes the classes in which you can interact with your teachers, you can ask your doubts then and there. You will get structures, pdfs for homework and the study material. There will be live test and there will be physical notes. These are the notes written by the teacher. And my personal favorite of these three programs is smart. In smart you will get mock tests and plus you will get one-on-one mentorship. These two are my favorite features which you guys will get in the smart. So I would recommend you guys to go for the smart course. And then if you want to have an edge over your competitors, and if you want to really outdo yourself, you can join a proficient batch. You can join a proficient batch for that. All right. So that's it from my side. I hope that I will see all of you in tomorrow's lecture. uh, we will be doing radioactivity and we will also solve a lot of questions on the same topic. All right. So thank you so much, and I hope I will see you in tomorrow's lecture. Have a great day everyone. Have a great day.